Sedimentary rock layers begin by being horizontal, but under stress they will fold into anticlines and synclines. Geologists want to describe the amount of folding and tilting, and to do so they use the term dip and strike. Here we have a tilted rock layer. The rock layer is dipping at 45 degrees. A very easy way to remember what the dip is to imagine that it's raining out and that water is dripping down the rock. The direction in which water is dripping is the dip, and the dip is measured from a horizontal surface. Here we have a horizontal surface represented by the top of a body of water. And you can see that the angle from that horizontal surface and the tilting rock layers is 30 degrees. So once again, the dip is the angle from the horizontal that a rock layer tilts. If the rock were vertical, it would have a dip of 90 degrees, whereas horizontal rock wouldn't dip at all. Its dip would be 0. Geologists also want to describe the direction in which the rock layer are tilting. In this you'll notice that we've got north. If we wanted to, we could always put in west, east, and south. And we have a tilting rock layer. The compass direction is given by the strike. The strike is the direction of an imaginary line made by the intersection of the dipping rock with the horizontal plane. In other words, this line right there. That has a strike. In this case, the strike of this rock is north. That direction. Well, I'm sure you're saying to yourself, well, how come that can't be south? The answer is, sure, it could be. But geologists like to keep things simple, so we just say north, and don't worry about it. So what line here represents the strike? Well, it would be from E to F. There you go. Here we have what's known as a block diagram because, hey, it looks like a block. The sides of the block diagrams are cross sections. So this cross section here shows us that we have a clear syncline and an anticline. The other side here doesn't show that it's a syncline and an anticline. So not all cross sections will give you the exact same information. The top of it is called a geologic map. And on that geologic map we can put symbols that have little numbers here. Those numbers are telling you the dip. But the symbols will tell us even more than that. In this case, we have our syncline. Here's the axis of the fold where it changes direction. It's dipping toward the axis on the syncline, but on the anticline, it's dipping away from the axis. Notice from the side view, we can tell that the youngest rock layer is the dark brown at the surface, and the oldest rock layer is this orange. So the angle at which the rock is dipping is going to be different along different parts of this geologic map. In the real world, however, the surface of the Earth is not a perfect horizontal surface. So the way that the rock erodes can affect how thick the rock layers look. Notice layer 2 is a reasonably thin layer. But on the geologic map, it looks thin here and very thick there. That's because what appears at the surface is affected not only by the thickness of the rock layer itself, but also at the angle at which it has been eroded. These are the geologic map symbols that we tend to use. Now, if you've got color, different rock layers are given different colors. But if color's not available, there are some very standard things, and they're not terribly surprising. That shale has little lines in it, and sandstone looks like sand, and conglomerate looks like, conglomerate. And metamorphic is all nice and wavy. What I want you to get out of this is this symbol right here, the strike and dip. The strike is the long part of the T. That is not given any word or any number. It's a compass direction, but it's always put on a map that already has the compass direction on it, so you don't have to write anything. But you have to show which way it's dipping and the angle of dip. So that's the short part of the T, and there'll be a number Also, we have symbols for anticlines and synclines, as well as for various kinds of faults, which we'll discuss later. So we have here rock layers dipping toward this brown layer and away from this pink layer. So if you were to imagine from the side, it must be dipping down like this and up like that and back down again. The center of the syncline, in this case, would be brown. If you imagine these layers and then cut off at the top, that's going to have the center of that syncline, this layer X and layer Y. X would be brown and it would be younger. Here also we have the symbols for the axis of the syncline. Here's the axis where it changes from one direction to the other. And these arrows, if arrows go in the same way that the dip goes in. And so these arrows tell you that this is a syncline. The arrows going away from the axis of the fold tell you that this is an anticline, and yet again another syncline. Here we have an anticline, but the two limbs of the anticline have different dips. The left side is dipping 20 degrees, while the right side is dipping 55 degrees. In this case, we have it's asymmetrical, and the axis of the fold is at an angle. If you were to see this on a geologic map, it would look like this. Once again, this is the symbol for an anticline. Sometimes the rock layers can get so folded, they can fold vertically and then fold over so they look like they're going in the other direction. That's what happened here. This rock layer here was once horizontal, and it dips straight up until finally it dips so much it looks like it's dipping 75 degrees in the other direction. How do you show that? You make this little flippy thing that it looks like it's 75 like this direction, but in fact it got there by going all the way up to 90 and back in the other direction. Here we have a symmetrical anticline, but the axis of the fold itself is plunging down away from us. We can even measure the angle of that plunge. If you were to see it in a block diagram, you can see from the side that it's going downward. But the top of it, or the geologic map, you can draw in the axis of the fold and show that it is an anticline, so you get little arrows, but you can also have an arrow showing the direction of the plunge. So here we have anticline, syncline, anticline, and as they are eroded away, you get this pattern of V's pointing either away from the plunge or toward the plunge, depending upon whether it's an anticline or a syncline. So whenever you see this V pattern on the surface, you know that you have plunging anticlines and synclines. Once again, a block diagram. You have the diagram showing the direction of the plunge, both of the anticlines and synclines, and the V's coming either toward us or away from us. What do you see here? Well, that V pattern at the surface tells you that it must be plunging, and from the side view we can see that, of course, it's an anticline. That pattern of V's can even be seen from space. Here you can see in a Google Earth image of Pennsylvania. Pennsylvania contains the folded mountain chains of the Appalachians. And from this image, you can even imagine the stress that created those folds, where North America got smashed by a collision with Africa. But hey, that's another story.